You're in a Palace 3 for the Breaking Things track. And this is the Are You My Type presentation by James Forshaw.
Hi there, sorry about the short delay, computer problems. So, what am I here to talk about? I'm going to talk about the research I did which ultimately resulted in the Microsoft Bulletin MS-12-035. And this was issues related to .NET binary serialization and the ability to use that to attack remote services or break out of partial trust sandboxes. It's also worth pointing out that actually some of these issues have only been fixed, have only been mitigated and not actually been fixed. So there's still some fundamental problems in .NET which are sort of hanging around which cannot actually be remediated in an easy way. So the obligatory company slide, I'm afraid, before I get onto the real tech. I work for a company called Context Information Security out of the UK. We also have offices in Germany and Australia, but we basically do three main things. Research, which obviously this sort of thing is an example of. We also do our assurance stuff, which is your standard pen testing and that kind of typical security work. And we also do response. So if you've been hacked, we'll come in and try and help you and try and work out how they got in and hopefully stop them getting in again. Anyway, so what is serialization? It's sort of a mechanism to transform a data structure of some form which can be then stored and transmitted and then later recreated at another time or location. So being a quote, who said that? Well, I just said that because I couldn't find a better quote than that. So why would we care? What is it about serialization which might be a bad thing security-wise? Well, we only have to look at other technologies to sort of demonstrate the potential risks involved in serialization mechanisms. So you have almost the canonical example of serialization vulnerabilities in Java. I'm sure most people here, probably everybody here, knows about sort of Java serialization issues. If you were here in 2009, you may have seen the presentation on attacking interoperability done by sort of the IBM X-Force team about COM serialization issues. And also PHP is another example. There's an unserialized method you can call, and if untrusted data gets sent to that method, potentially bad things can happen. Now, .NET being quite a big framework has a number of different serialization mechanisms sort of built into the framework. First and foremost is the I format of serializers, so binary and SOAP, and they've been around since the very first version of .NET. And also included in version 1 was the XML serialization mechanisms. And this is a bit more sort of, binary serialization is very, very powerful, and which is sort of why I'm talking about it. XML serialization is considerably less powerful. You can only create public types, very, very limited, but in the scenarios in which you want to use it for, it's quite useful. And so does some others. As part of version 3, Windows Communication Foundation introduced the data contractor serializers, and 3.5 also had a built-in JSON serializer. But as I've said before, I'm here to talk about binary serialization. Now this is sort of baked in to the .NET framework, basically just sort of special support for it. But not every object can be serialized. If you, for example, had a reference to, say, a file or some unmanaged resource, it's not something you can just serialize. So at which point you actually have to say, I actually want my C# type or Visual Basic type to be serializable. And to do this, you must specify an annotation on that class which basically says, hey, I approve this for serialization and I will take responsibility for it. So this is some very simple code which represents how you would actually do binary serialization. And as you can see, there's actually not much to it. You create a binary formatter instance and you then just push the object you want to serialize into it and out comes a binary blob of data. So you can see why its power and its flexibility is quite high, and obviously that can lead to substantial misuse if it's not taken care of. Now, the end process of that, as I say, is a binary blob of data, and this is sort of a rough representation of that class previously, which we serialized. So the binary data itself contains the name of a library. So this is the DLL, effectively, which hosted that type. You then have a type name, so this was the serializable class, so that's recorded in there. Each field then is represented, so each basically member variable you can specify in the class is then represented by a named value. And then finally, in this case, the hello world string is stored as a straight binary blob in there. But of course, it is a potentially dangerous operation. The binary formatter can access private types, private fields of an object, and manipulate that and could fill it with junk data. So if you were to use binary formatter in some sort of untrusted scenario, so for example, you were reading byte stream off a socket and pushing it through binary formatter, there's always a risk that there could be actually a security issue with that. But surely the only time that's ever going to be a problem is you get your object back and your badly written code does something stupid with that resulting object. But it turns out that's not necessarily going to be the case. So the framework potentially has mechanisms whereby code will execute during the process of deserialization. And so in this particular case, this bit of code which is doing deserialization, you've taken potentially untrusted input into the system, and before you've even had an opportunity to stop that deserialization process happening, you've already been done over. And that's the sort of potentially risky scenario of using this mechanism. So one potential way that code can execute is by leveraging the custom serialization functionality. Sometimes you may not be able to specify exactly what you want to do just using the sort of default mechanism. The default mechanism will just take each of your member variables and serialize those individually into the binary stream. But sometimes that's not actually what you want. So one of the mechanisms the framework provides is you can implement this ISerializable interface. And this interface allows you to specify custom serialization and deserialization code to run at that point in the process. And in this case, you've implemented the getObjectData method, which is run on serialization, and you get a dictionary of key value pairs you can fill in with whatever data you like. And then on the other side, you implement a special constructor, which again takes that object and manually deserializes your object. But you can see how potentially if there's dangerous code in that interface implementation, something bad could happen just by the process of deserialization. So I did what anyone would do. I wrote a program to basically hunt for bad stuff. So in this case, I wrote a tool first and foremost to go searching for serializable types. And this is just an example of 5 of the main libraries in the framework and sort of the rough counts of the number of classes which are serializable. So, for example, MS-Core-lib, which is like the basic library, you have to have it in every .NET application, has about 681 serializable classes. Now, considering there's only about 1,800 classes in the entire library, that's a fair proportion. Over a third of the classes is serializable. Now, of those serializable classes, 268 have custom serialization mechanisms, which might mean you could do something bad if you can find something bad in there. Now, there's also other mechanisms, for example, callbacks. So there's general sort of on deserialization, run this bit of code, do some checking, that sort of stuff. And there's also finalization. Now, finalization is effectively destructors in the sort of C++ idea, but for .NET. And you'll see this similar. If you know Java quite well, you'll probably have encountered these as well. And these are bits of code which will run to make sure you can clean up all your managed resources before the object gets disposed of in the garbage collector. So in this case, there was 2 in MS-Core-lib. So let's actually go into finding some stuff which does something nasty. If I just want to start and just be malicious, well, this class kind of fills in that requirement. So you've got this class called temp file collection, and it contains a list of file names which are the output of a compilation process. So, for example, you compile some sort of source code and it generates temporary files which it keeps a collection of and makes sure that they get deleted at some point in the future. No guarantee when, but it will definitely do it at some point in the future. Now, this implements a finalizer, and the thing the finalizer does is basically just walk through this list of files and deletes them. So if an attacker can serialize a list of files in there and hand it to you, then when that object goes away, it's going to start deleting arbitrary files on your file system, even though you haven't actually interacted with the object at all. So I'm just going to do a demonstration, hopefully, assuming this works. Possibly. Okay. So this is on Windows 7, and I've got a serialized temp file collection class. And right at the bottom, this is our file we're going to delete, important data.txt on my desktop, which is sitting there waiting to be molested. So if I run this bad application, so this bad application just takes a file and pushes it through binary formatter. It could have been a socket application or any other sort of type of application which will take an arbitrary binary stream. And if we load that file from the desktop, it says we got a temp file collection object back. That's great. But it doesn't seem to have worked. The file is still sitting there. Well, that's because the finalizer isn't going to run immediately. It waits until the garbage collector actually picks up and decides to destroy that object. But if we actually close the application, our file has now been deleted because it has to have run the finalizer to make sure everything is being cleaned up appropriately. Okay. So there must be ways of protecting against this. Well, you can be a bit more defensive in your development of any application which uses binary formatter. And one of the ways is you can specify this special serialization binder class, which allows you to basically just say, I accept these types are valid and these types are not. And the big one is just don't trust binary formatter with data coming from the outside world. And you can also use plenty of other stuff. As I've shown with the previous slide, there's a number of serialization technologies present in .NET. There's things like protobuf.net, which came out of Google. So there's plenty of other techniques you can use for serialization. But of course, you've done all this. You've removed the use of binary formatter. You've, say, used protobuf instead. So you're safe. There's no possible way you can be attacked. Well, because it's such a fundamental serialization primitive, it's also used in a few other technologies which have been around since the very first version of .NET. So if you're using .NET remoting, for example, you may be at risk. Or if you're using partial trust sandboxes, you may be at risk. And this is all happening inside the framework. You don't even actually see it. You don't have any reference to binary formatter in your code, but in fact you're actually using it or without any actual knowledge. So let's go a bit into how .NET remoting actually works. Because the first thing I'm going to look at is actually attacking remoting services. So remoting services has the concept of these application domains. These are built into .NET. They're fundamental .NET objects, part of the framework itself, and act as isolation mechanisms for objects. You cannot directly pass an object from one app domain to another without any other sort of mechanism in order to achieve that feat. Now, if you want to actually talk to a remote object, so imagine one of these domains is actually sitting on a system somewhere the other side of the world, for example, connected over the internet. It will be publishing some sort of well-known service on say, a TCP port 1024, and another app domain wants to do some work on that. So it creates first that TCP channel to act as the communication carrier, and then it has to package up all the request data. So it has to know who it's going to talk to at the other side, and also all the parameters have to be packaged up as well. So it packages that up, sends it across the link, and the well-known service will unwrap that and action that particular function call. Then obviously it's a symmetric process, so you can pass it back, any return value gets thrown back across the link, and there is your remote call. But that does still leave the question of how parameters themselves get across the link. Because I've already said that an app domain, you can't pass objects directly between app domains. So in this case, there's actually two ways in which you can pass objects, which are built into the framework. And if you've used any other sort of remoting technology, such as RMI in Java, you're probably very familiar with this sort of concept. So the first one is Marshal By Reference. So in this case, your object never actually leaves your app domain. But what it does do is it creates a special object which has all the information to refer back to the original value. It is actually then that which gets converted to some binary blob and passed across the link, where it can create a proxy object to talk back to the original object in your app domain. But sometimes that's not appropriate, so there's another way of doing it. You can, if your object is serializable, then it will actually get directly converted to a binary blob, and when that gets passed across the link, it actually recreates a copy of that object at the other side. So any then function calls on that object will be local to that app domain. But obviously, I've talked about binary serialization. You can kind of guess what technology it uses to do this binary transformation. So we had the malicious, just the general malicious attack, deleting files on your file system. So let's go for something a bit more active. Because it's a remote service, we may want to actually try and do something particularly nasty to it. So in this case, I found a class called FileInfo. Now FileInfo, as its name might suggest, provides information about a file. And it contains things like its path and its file size, all that sort of stuff. But during its custom deserialization process, it first has to make sure that path is canonicalized. So in order to get rid of .. and all that sort of stuff, it basically canonicalizes the path. Now, it does this in a really, really sort of simple way, and just it doesn't touch the file system, or it shouldn't touch the file system. But this is actually a very simplified version of that code. It basically splits the path into individual components, and if one of those components starts with the tilde character, it assumes that perhaps that file name is actually a short path, so an 8.3 Windows short file name. So in order to make sure it's got the definitely correct path, it pushes it through the Windows API of getLongPathName. Now, getLongPathName has to refer to the actual file system, because otherwise, how's it going to do that translation? So what if we passed in a file name of //evil/tilde_share, for example? Well, what that ends up doing is your application starts making SMB requests back out. And there's plenty of, you can go to Metasploit, load up the SMB relay module, and you can then potentially exploit this. So you can either do credential reflection back to the person who generated that request, or at least you used to be able to, or you could relay that authentication mechanism to another system on a domain and attack something else that way. But nothing is ever simple. This entire process was anticipated by the original designers of the .NET framework. So this is a page in MSDN, and basically the first sentence is basically saying, in order to actually work out whether the parameters you're passing are valid, you must have deserialized these parameters. And so you've got kind of a chicken and egg problem, and you could end up with automatic deserialization, and as it quotes, might try to exploit the moment of deserialization. And you can be guaranteed that's exactly what I want to try and do. So it implements type filtering. So when I try and send my dodgy FileInfo class across the link, well, the remote server just says no. It doesn't match up with a set of rules it has in the framework which says these are valid objects to be deserialized. So we need a way of bypassing this. And one of the things I found to do this is the dataset class. Now, the dataset class is a in-memory database. It can contain multiple tables, but it has to do some clever manipulation of its serialization in order to handle the fact that it's able to serialize its tables both as XML and as binary blobs. So what it does is it does serialization in a two-step process. So for example, in this case, we have a data set. The star represents like our bad file info. And the first thing the data set does is serialize that file info to a binary stream. It then actually stores that in its outer wrapper, serialized wrapper, and it's that which gets passed across the link. And when the deserialization process gets processed in the type filtering binary formatter, in fact, all it deserializes is an array of bytes, which is perfectly legitimate for the secure lockdown system. But then the actual dataset deserialization code kicks in. It creates a privileged binary formatter and proceeds to deserialize your file info class, which then ends up you doing an SMB request out and potentially doing something nasty. So I'm going to demo it. It's a demo on XPSP2 just because that's prior to the fix Microsoft did on SMB reflection. It just makes the demo look slightly nicer. But you can still use it for things like information gathering because it will go out and say who's actually run that piece of code. Or you can use it to sort of like brute force passwords if they're still running operating systems generating the landman hashes. So, I have here my XPSP2 machine. Just expand that out slightly. And on this machine, I'm running a very, very simple server. I think the actual remoting code is about 5 lines, something like that. So there's no actual implicit sort of functionality being used which says I'm using binary formatter. So if I actually run up a client for this, so this is actually running under Mono because Mono implements basically pretty much everything according to the standards. And so I can just to demonstrate it's actually working, let me send just a simple message to the server, and it says hello Black Hat on our server. So instead, we want to run this SMB relay. So I've got a copy of Metasploit running the SMB relay exploit payload. So if we go back to here, and in this case we send our file info class, so 172.168.1. So this is pointing back to the machine I'm hosting this on. If we send a request, we now suddenly start seeing loads of stuff going on in the Metasploit session, and we get calc to appear. So, fairly simple. So again, how can you protect against this? Well, the main one, or certainly the Microsoft recommendation, is just don't use .NET remoting. .NET remoting is considered to be an obsolete technology, and so Windows Communication Foundation is the way to go. Also, just don't expose it to the internet. You can add authentication mechanisms to it as well to prevent just arbitrary people connecting to your servers. But it's also worth remembering that the process is symmetric. So anything which works upwards towards the server probably also works down as well. So if you can impersonate the server in some way, either ARP spoofing, DNS spoofing, whatever, you can then start attacking clients instead, at which point the authentication mechanism isn't necessarily going to help you. So now on to probably the most interesting bit, the sort of breaking out of sandboxes. Now it's interesting that basically the infrastructure which implements .NET remoting is used again for partial trust sandboxing. That whole isolation aspect is a very useful feature to prevent people gaining access to objects outside the boundary of our AppDomain. And you can also assign permission sets to these application domains which restrict the code, what the code can do running in it. So what will usually happen, you'll have a host domain which will create this partial trust limited permission domain. And that can then create untrusted classes coming from untrusted libraries somewhere. And this is used in a few technologies. So for example, there's ClickOnce. And there's also XAML browser applications, which are basically a browser-hosted .NET program. Now, there's various different permission sets you can specify. So, for example, you can say the code can only access files in this directory, or it can only open web requests to Google, for example. But there's also, as is common with these sort of sandboxing mechanisms, there's also some God-level privileges. The stuff which basically, if you give it to untrusted code, you may as well not have a sandbox at all. So there's things like, can I call arbitrary Windows API functions? If you can do that, you can probably fairly easily break out the sandbox. But unfortunately, access to serialization services is considered one of those God-level privileges. So there's no, well, unless you've implemented very badly your sandboxing, there's very little chance you will actually have access to serialization in your partial trust code. And that represents a problem. But we know from remoting that all we actually have to do is find some way of getting an object to transition from one of those application domains to another, at which point the framework will actually do all the work for us. You'd think that would actually be quite a difficult thing to achieve, but it's actually not as difficult as you'd imagine, because the boundary is fairly porous. Part of the use of .NET remoting is the fact that it's almost transparent. You don't realize you're using it. But that also then leads to the fact that you can't easily audit which bits are using .NET remoting and which bits are not. So for example, in this case, XAML browser applications had a bug with its exception handling. So the browser host would basically start creating a host application, and in order to run the code in partial trust, it would have to transition across that link into the other code. Now, this is still then the same flow of execution. But that execution goes up and eventually leads to something we can control. So in this case, this is evil XBAP, and someone's clicking a button, but you don't actually have to have user interaction. Just running the code is sufficient. If that piece of code creates an exception object, exception objects are already serializable objects. So it throws that and it starts going up the stack, trying to find something to catch that exception, to stop the process from crashing. And it goes all the way up to the transition point between the app domains. And the framework then goes nicely, well, no one in this app domain serviced that exception, so maybe someone over the other side will do it. And so it serializes it, throws it across the link, and recreates it at the other side. And that gets us our round-trip serialization. And it is pretty much that simple. This 3 lines of code is enough to get an arbitrary object round-trip serialized in an XAML browser application. And this was one of the bugs which was fixed in MS 12.035. But there's still a problem. Before, we could just specify the binary stream itself, so we could manipulate it in any way we liked, manipulate internal states of objects to do anything we wanted. But we can't do that from partial trust code. Partial trust code is not supposed to be very privileged. If you could manipulate the internal state of objects, that's a bad thing. So we cannot directly provide that binary stream, but there must be a way of partial trust to manipulate that process. And to do that, we just have to go back to our ISerializable interface, which has been so fruitful already. And one of the things the custom serialization process allows for is the ability to change your type. Now, this might be used, for example, if you need to transport your object as a different type across a boundary, and then when you deserialize, you can then recreate your original type again. So it allows you to just set your type. It has a set type method. But unfortunately, there was no actual restriction on what type you could specify. So if I wanted to create a file info class, I could just set the type of that, fill in some fake serialization data which would match up with what it was expecting, and it would actually deserialize to that, or deserialize into a different type to what it's serialized from. And this is just a sort of really simple demonstration. So in our partial trust domain, we have our exception, and imagine our green dot is our custom serializable class. It gets packaged up, it's changed its type, and actually now on the other side, it's become a completely different type to what you put in. Now we could use this for various things. We can obviously do it, the S&B reflection stuff, but let's face it, that's not exactly the most interesting things to do, especially as it's not something you can easily do now with the fix on reflection. So I wanted a different way. What if I could get hold of that object? If I've just created a potentially corrupt and manipulated object, if I can get it back and call methods on it, because I got code running in partial trust, perhaps I can do something with that. And so I found a class which just did that for me. The evidence-based class was added in .NET 4 and is used to formalize the mechanism of evidence. I unfortunately don't have the time to actually describe what evidence is, but it's basically sort of a use for trust decisions. And it's marked as serializable, but it also implements a method to do a deep clone of that object, because it might need to copy these objects around a bit. So this is the entire code for the clone method, and it looks fairly similar to code I've already shown up on the presentation. So it's serializing the current object into a stream and then basically pushing that back through the binary formatter to spit out a new copy of that object. But this wouldn't have necessarily been a problem, because if I called that, because of the way .NET security works, if the caller of that method didn't have permissions to do serialization, it wouldn't actually make a difference. But unfortunately, it was annotated with a special override which basically says, actually no matter what people call me as, I don't care what their permission was, assume I have serialization permissions. So that's a bit of a security problem. So exploiting it is very simple. If I derive a class from EvidenceBase, just create a new class, fill it with a member variable which contains the object we want to get back, but the custom serializable one, so it will craft it. If we call the clone method, the round-trip serialization process will ensure that in our own domain we've managed to get hold of that corrupt object. And that's then we can do something with it. So to fill in the final piece of the puzzle in terms of getting remote code execution, breaking out of the sandbox, we need a type which we can corrupt in such a way that it causes a security problem. And for this I chose delegates. Now delegates are something which has sort of been built in since day one of the .NET runtime. Effectively are just sort of fancy function pointers, but they have special treatment in the framework for performance reasons. They effectively boil down to, when they're jitted, to straight function calls. But it's also serializable, which makes it very, very interesting. Especially as it also has an interesting property called multicasting. Now a delegate will normally just represent one call to one sort of method, a sort of standard function pointer. So in this case we've got a type of our delegate which is taking a word-sized integer pointer. But what we can do is we can actually join multiple delegates together into one single delegate. And then when we call that method, both those functions get called, one after another, with the same parameter. But what if we could actually specify two different types for these delegates? So in this case, we now have a string delegate, which takes a string, but we also have our pointer one. We try and combine those together, and the framework says no, because having those two types would cause type aliasing issues, which basically could be exploited. But what happens when we do a serialized delegate? What will this do if I actually call this method? Well, it turns out it will do that. So this is dump out a WinDebug. In this case, ECX points to that fake value we specified, because basically it's been passed on the stack, there's been a type confusion issue, and so effectively you've now just got a string which is represented by the pointer of 1, 2, 3, 4, 5, 6, 7, 8. That ultimately leads to a vtable lookup and call, and you can see from the stack but it's clearly massively confused as to what it's supposed to be doing. It's calling through an int pointer delegate into a string method, and that shouldn't happen. So I'm just going to do a demonstration of that in ClickOnce, so using the EvidenceBase class. Come on. So if we start this up. Make sure I have my web server running, otherwise it's not going to do very much. Okay. So if we run this from the browser, we get various dialogues as it starts up. But basically this is going to be creating an application on the desktop which is running with a heavily restricted permission set. And you actually see this being used even now. For example, if you install Google Chrome via IE, it will actually use this ClickOnce mechanism to drop the installer on your system and install Chrome for you. So obviously there is a warning dialog associated with that, but we also get this big flag, don't type your passwords into this application because it's probably malicious. We can see a big go button. So this go button will effectively go and kick off the evidence-based vulnerability, run some shellcode by doing some corrupt delegates, type aliasing, all that sort of stuff, and we end up with calc. But it doesn't really end there. Evidence-based is a bug. It's a clear bug. You shouldn't be able to, either the method shouldn't have asserted the serialization permissions, or you shouldn't have been able to derive your own object from it if you're coming from partial trust code. And it was fixed. It was fixed in MS-12.035. So what if we could actually achieve the same result without any actual specific bug in this sort of sense? It would work in every version of .NET, because obviously evidence-based only came from in version 4, and also, crucially, difficult to fix just because I'm feeling nasty. So again, we go hunting for interesting objects. And one of the things I found is the hash table object, or hash table class. And this is something which has been in since version 1 of the framework. Basically is a key value dictionary and was done before you actually had a proper generic dictionary which came along in .NET 2. And it serializes its keys and values, but it doesn't actually serialize its hash table because due to the way in which it's implementing the hash function, it cannot guarantee that those values will match up when you, say, deserialize from a file at a later date or on a different machine or a different version of the framework. There's no actual guarantees in that to make sure that you're actually using the right thing. So it calls a rebuild hash table function. And this thing uses a special object called an higher quality comparer, or at least that's the interface which implements it. And this can be specified by code. You can pass it in a constructor and say, I want to use this special comparer as my mechanism to generate these hash values. And so it gets serialized with the hash table, because obviously once you get to the other side, you may actually want to use the same thing you used at the other side. And what it does is it goes through every single key in the collection and calls the getHashCode method on this comparer, which is interesting. So what if this object was never actually serialized? So this is how you can basically do it without ever having to find a specific bug. So in this case, we've implemented our own custom equality comparer, but crucially, we've made it so it's a Marshal By Reference object. That means that object will never actually leave our partial trust sandbox. So we throw our hash table across the boundary using the XBAP bug I've already mentioned, for example, or any other mechanism to cross the boundary, because there's still ways you can affect this. And I get serialized across and recreated on the other side. Now obviously, we've now got our bad object created in the other domain, but obviously we can't access it because it's sitting in the host application domain. But now the hash table deserialization code kicks in. And this is where it gets interesting. So it goes through each of its keys, passes it to the getHashCode method. But the getHashCode method is implemented inside our Marshal By Reference object. So it has to serialize each of those keys back up and pushes them back across the boundary. And because effectively we've broken the symmetry of the serialization process by doing this type aliasing issue, when it goes back across the boundary, it doesn't realize it's got to convert it back to our custom serialized object. It now just thinks it's actually this corrupt delegate. And you can use that to get back your object. So, final demonstration. So in this case, we've got a XAML browser application. And you see it's hosted inside IE. There used to be actually a Firefox plugin or MP API plugin for it, although I believe that's now deprecated. And come on. Taking its time. Right. So again, just got a simple start button. You can also specify the command if you're so inclined. And to actually better demonstrate it in action, I've also added a special marker object. So this will basically pop up a dialog box saying at what stage of the process it's currently at. So if I click Start, we first get our object is being serialized in the partial trust app domain. Makes sense? It's just a hand across the boundary. So we click OK. It's now deserializing in the default app domain. And this is the hosting app domain somewhere else on the system. Click again. Well, now we're starting to go back the other way again. Now it's starting to serialize it again. We finally get deserialization in the partial trust app domain, at which point we get calc to appear. And we can see from basically the fact that it's would now normally show this exception dialog, but as you can see, it actually exploited it before it even finished the exception process, because we were actually doing this exploit during the process the exception object was being deserialized. So before the hosting code has even realized it's got an uncaught exception to catch. So it's tricky to protect against that, because basically we've not technically used any real bug. Okay, the exception trick is a bug and has been fixed, but there's other ways in which partial trust code can do that. And it has massive potentials for back compat issues. So effectively Microsoft's fix was now you cannot do this type aliasing anymore. If you are partial trust code, you can no longer just arbitrarily set any object type you like. But also probably the biggest one is basically Microsoft have blocked any use of partial trust.NET code from the browser, because it was just too much of a security issue, and so XAML browser applications are effectively banned, certainly from the internet zone. You can still use ClickOnce, but obviously you saw that dialog which popped up, and you could argue that if you click through a dialog, you could have clicked through a dialog which says, do you want to get owned, at which point it doesn't really matter. So there was a lot more to the bulletin release than was actually just posted just in the CVEs. So there was only 2 CVEs in it, but there was actually quite a few different fixes implemented in that bulletin release. Now, attacks from partial trust code have been mitigated, but .NET remoting is still something which potentially you could attack if you found the right system. And there's still a number of objects which, if you could get them deserialized, would do something potentially nasty. So that's the end of the presentation. If anyone's got any questions, if you want more technical details, the white paper should be on the CD, which has code examples of how to create the corrupt delegates and all that sort of stuff. So, any questions? No? Cool. Thanks very much.